The company we engaged to convert our Rocky to electric cancelled the contract, which was both painful and expensive for us, but it has been a blessing in disguise because it means that we've now had to go back and start all over again. So we've picked up all of the bits and pieces, and we've now have a Rocky which is basically empty. There's nothing being installed in the car, so we're going back to square one to redesign it, and I believe we're going to have a much better outcome as a result of that. And in this video I'm going to be talking about that redesign process in detail. So from the manual we have quite a bit of information about the vehicle that we're going to need. The Commonwealth Vehicle Standards Bulletin 14 specifies things that we need to satisfy in order to get it registered. And the West Australian Department of Transport also has some requirements that need to be met. So, bearing in mind these requirements, we're going to try and keep the vehicle to its current gross vehicle weight and find some options that are going to allow us to have a reasonable range and performance without having to do complex redesign of suspension and tyres and so on. So we're looking at two options. One is a net gain Hyper 9 motor going through the existing gearbox transmission system. The alternative is a Tesla large drive unit which is centrally mounted and has a differential that will drive the forward and rear axles of the vehicle. So the first thing is to decide whether each of these motors is able to provide sufficient torque to the driving wheels to provide the same performance as the original diesel motor. So these graphs show that the net gain motor is able to provide almost twice the torque of the original diesel motor at any given gear ratio, but this is a peak value. The continuous value is about a third of that, but it's still comfortably within the range of what we'd expect. According to the Commonwealth design rules, the Tesla motor would have to be down rated to a maximum of 288 kilowatts to retain the allowable power weight ratio for a 1986 vehicle. So, but even so, this graph shows that it would easily provide at least double the torque of the diesel motor at any gear ratio. And again, the continuous power is about one third of that, but it's still able to comfortably meet the requirements of the original diesel motor. There are two battery chemistries available. One is the lithium ion nickel cobalt battery, such as those used in Teslas at the moment, and there's also the lithium iron phosphate batteries. The Tesla ones are second-hand, whereas the iron phosphate ones would be new. So although the Tesla batteries have a higher energy density when new, they're probably going to have to be down rated because they've already had a life and will not be able to have the same capacity. So there's probably not a great advantage in energy density. They also have fewer life cycle charges compared to the lithium iron phosphate ones. they become unstable when hot. They can't be fully discharged. So we've decided that we're not going to go for the Tesla battery packs, even though they're probably somewhat cheaper than the new batteries, but they just aren't going to provide the same performance. So we're going to go with the lithium iron phosphate batteries. So we now do a mass balance, work out what we're taking out of the vehicle, what we're keeping in, to work out how much battery mass we can add to the car to retain the existing gross vehicle mass. Given that we've basically kept everything the same, we've reduced the payload down to 100 kilograms from 120, but otherwise everything's pretty much the same. So for the net gain, we worked out we can put in 370 kilos of battery. For the Tesla option, we can put in 380 kilos of battery, which is about 10 kilos more, mainly due to the reduced weight of the transmission using a Tesla option. So now we have to see how many batteries we can actually fit in based on the space available. We have available for storing batteries are in the engine bay. We've got an upper and lower battery box in the engine bay, and we have another potential battery box where the fuel tank was. So for the net gain battery, we can have 66 batteries. So it's two lots of 33 batteries in parallel, produce about 106 volts, and that weighs 347 kilos and gives us 64.2 kilowatts. For the Tesla, we can fit in 190 batteries. That's so two lots of 195 batteries, which gives us 300 volts, because we need different voltage for the Tesla, which weighs 380 kilos, that's right on the upper limit, and gives us 63.6 kilowatts. So to get that, so we've realized that to get that 300 volts for the Tesla motor, we need more batteries, but smaller ones, to be able to get the 300 volts, and that's a slightly less efficient arrangement. So we're coming to the conclusion that the net gain option is going to give us more battery power and a better weight, at a smaller weight than the Tesla option. That we have a battery box in the engine bay and one where the fuel tank is. With the net gain, we have this is the weight of the batteries for the net gain option and for the Tesla option. And this is the effect on the weight distribution of the vehicle. And so it doesn't make a big difference. There's less than 10% change in the weight distribution between any of the battery options and the original vehicle. So that gives us comfort that it's going to be acceptable from a registration point of view. The other consideration was that the Tesla motor hangs a little bit beneath the vehicle and would reduce our ground clearance, whereas the net gain option doesn't change the ground clearance. So I'm now doing a range calculation for the vehicle, assuming we're using the net gain option, which is a 64 kilowatt hour battery, charging it to 80%, but being able to discharge almost to zero without damaging the battery. How far can we get? And that's based on the graph provided in the Rocky manual, which is giving me an idea of drag, air resistance and tyre resistance at given speeds. We converted this to a mathematical formula and can calculate how much power the electric batteries are going to have to provide to drive the vehicle at any speed. Note that speed has a massive effect on the range. So 100 kilometers an hour, somewhere less than 200 kilometer range. At 20 kilometers an hour, you're getting up to 400 kilometer range. So it's a matter of how you're prepared to drive. If you're really desperate and have to fully charge your battery, you get about an extra 40 kilometers of range. So that's it for this analysis. The next video will be looking at the design of the electrical components for the system.